Welcome to MAth317 Operations Research, probably around day 21. Before class we were talking about perspective. I'm going to detour a little bit from what I was going to talk about and give a geometric argument on special relativity. I was not planning on doing this, but given the perspective comment, how many of you have done anything with special relativity? Excellent. So one of the big results in special relativity, yeah, nice. I saw your hand was up. There's a joke that after Einstein announces general relativity, someone goes up to one of the great physicists of the time and goes to him and says, do you know that there are only 3 people in the world who understand Einstein's theory of general relativity? And the great goes, really? I wonder who the third is. But in special relativity, one of the strange things that you learn is that if you are traveling relative to somebody at rest, your length contracts. And so what's interesting is that it's only happening in the direction of motion. And given that we're going to be talking about directions and whatnot, I thought I would share, based on the banter beforehand, Einstein's thought experiment that proves length cannot contract perpendicular to motion. So how many have seen this thought experiment? So it's done with trains because Einstein's theory of relativity is from the early 1900s. This was the fast mode of transport. The fundamental principle is physics must look the same from all different frames of references. So imagine I'm a good artist, and you have a train on some tracks. And you put 2 cans of paint right on the back of the train, so if the train is at rest, the paint will fall on the tracks. Now imagine the train is moving at 3/4 the speed of light, say, relative to somebody who's just going at the station. Okay? If length contracts perpendicular to motion, from the point of view of the person at rest, the train is going to be thinner, and the paint will land inside the tracks. From the point of view of somebody on the train, however, the tracks are stationary. And so the distance between the tracks contract, and the paint would land outside. Now you just need a way to get them in the same frame of reference, so we'll put some mountains over here. So the train crashes into the mountains, and now the person on the train and the person on the ground can compare. And you can't have the paint both inside and outside the train tracks. So this proves that you cannot have contraction perpendicular to the direction of motion if you assume that physics has to be the same. Right. From this now I want to go to another geometry problem, Lagrange multipliers, and leading from this into multi-objective programming. We talked briefly about Lagrange multipliers, or was that a video I had you watch at home?
We mentioned it.
So how many people can prove the Lagrange multiplier, that if you want to find the max bin of, say, f of x subject to, say, g of x equals c, you need the gradient of f to be some multiple of the gradient of g. So as an example, let's say we have g of x, y, z is x squared plus y squared plus z squared. So if I look at g of x, y, z equals c, what kind of surface is that?
Sphere.
Sphere. For any choice of c?
Except for 0.
So as long as, so then you can ask, is a point a sphere? Definitely we want c to be at least non-negative. Probably we want c to be positive. So if we take, say, some value of c, we have a nice sphere. What is the gradient of g? This is dg dx, dg dy, dg dz. And because I want my life to be simple, I chose a really nice function to differentiate. I just get 2x, 2y, 2z. So I get the vector 2x, y, z, or you might sometimes write it as 2 times the radius. So the gradient of g points in the normal of the surface. So this is not quite a sphere, but it's close, maybe from a good distance. And so the gradient of g is going to be the normal to the sphere. And you can see that it's in the same direction as the radius. It's just pointing further out. So what does it mean? Let's take the North Pole. That's a nice simple point. What does it mean to find a maxima or a minima with a constraint? If I didn't have this constraint, if I just wanted to find the maxima or the minima of f, I would just look for places where the first derivative is 0, and then I would look at boundary points. Well, in the real line, how many boundary points can you have at most? Two. It's not a big deal, right? Checking boundary points in the real plane, not a big deal. We don't really have to develop an advanced machinery to handle it. There's 2 points to check. As soon as you get to a two-dimensional surface, however, you can have a boundary with infinitely many points. Sometimes what you might do is you might parameterize the boundary. Maybe it's a nice curve, and then you can use one variable calculus on the boundary. As you start getting higher and higher and higher, it starts getting more and more complicated. So what does it mean to find the max-min subject to this constraint? It means I have to always stay on the surface, and I want to keep moving on the surface, and I want to see where can I move and have my function be largest. Well, at any point of time, the gradient of f points in the direction of maximum change of your function. Think back to calculus. If f prime of x is positive, then if x is increasing, your function is increasing. If f prime of x is negative, then as you increase x, f decreases. So by looking at the sign of the derivative, if you want to increase or decrease, you know which direction to go. So if you want to find a max or minima, you only have one option in one variable calculus. You need the first derivative to be 0, unless, of course, you're at an endpoint. But if you're in the interior part of the space, the only way you can have a max or minima in one variable is the first derivative is 0. Otherwise, well, if I go in one direction, I'm increasing, and if I go in the other direction, I'm decreasing. It can't be a max, it can't be a min. Now let's look at what's going on this constrained optimization problem. We have to stay on the sphere. Imagine at this special point, the gradient of f is pointing in this direction. So here's gradient of g, here's gradient of f. So I can write my gradient as something of f as something in the direction of the gradient of g and something perpendicular. And what would we like to use for perpendicular to sound more fancy or highfalutin? Orthogonal. Yeah, it sounds so much better, right? So I can write it as some component tangent and in some direction normal. Well, as long as my gradient has some component tangent to the surface, it means I can walk in that direction and I'll stay on the surface. And my function will be increasing. And if I go in the opposite direction, my function will be decreasing. So what we can prove from this very easily is that if we want to have a candidate for a max or minimum, a candidate, the only way we can have a candidate is if the gradient has nothing in the tangent direction. Because if it does, just move in that direction and you increase, move in the opposite direction and you decrease. This gives you candidates. Is a candidate the same as saying it must happen? No. No. Right? This is the difference between necessary and sufficient.
What do you mean has nothing in the tangent direction?
So it means that the gradient of f has to be entirely pointing in the direction of gradient of g. There's no component over here. And that's where this relationship comes from. The gradient of f is some multiple of the gradient of g. These two vectors are in the same direction. Does that choice of letter remind you of anything?
Eigenvalues.
Reminds you of eigenvalues. Right? We want them to be in the same direction. You can hear the word same as you do in eigenvalues with eigen. And then the question becomes, how easy is it to solve? So imagine we have 3 variables. We're going to get 3 equations from this. But now we have 4 variables. We have x, y, z, and lambda. So we have 3 equations, but 4 variables. We're screwed. Unless we can find a 4th equation. What's the 4th equation?
Equals c?
Yeah, g of x, y, z equals c. There are 4 equations and 4 unknowns. If you can only solve for 3 of the 4 unknowns, x, y, z, and lambda, which one would you sacrifice in a heartbeat?
Lambda.
right? At the end of the day, I care where is it having its maximum, where is it having its minimum. Lambda often helps me get that. But at the end of the day, if I don't find lambda, I don't care. Lambda is just a helping variable to get to the solution. But at the end of the day, I don't really care about lambda. Lambda does have some significance maybe in terms of magnitude, in terms of how much things are going. But I don't really care about the value. I care about finding x, y, z. Now, I mentioned that just because you have a candidate doesn't mean it actually has a maximum or minimum. So does anybody know what's the best function to look at in one variable where the first derivative vanishes, but you don't have a maximum or a minimum? X cubed, right? You could be different and do x to the fifth, but x cubed is good. So if you calculate, f of 0 is 0, f prime of 0 is 0. So when we take f prime vanishes. So we have a candidate for maximum or minimum. I may not be a great artist, but even I can draw this one. And here's the function, isn't that beautiful? X cubed. Clearly not a max, not a minimum. What goes wrong? The first derivative vanishes. Why doesn't it have a maximum or minimum? Yeah, the second derivative is also 0. F double prime of 0 is also 0. And that's what goes wrong here, so that you have to modify the first derivative test. And this is where the second derivative test comes from. If you just plot the first derivative, f prime of x, then what you see is it's 0 at 0. It's positive when x is positive, and it's also positive when x is negative. The function is basically increasing, stops instantaneously, and then starts increasing again. All right, so this is a quick review of Calc 3. All right, how many of you have seen this in Calc 3? How many people did not see this in their Calc 3 class? Or did not take Calc 3? Okay. Sometimes there's disputes as to what material to cover in calculus classes. I believe this should always be covered because of which department on campus? Econ, right? You really should not be doing high-level economics without having seen something like this. All right, so this is the finding the maximum subject to one constraint. Have we seen anything in our class so far where we are trying to find an optimal? Yes?
How does the last part connect to this?
Which part?
Just kind of this.
This is an example where you have a candidate, but the candidate is not a maximum or a minimum. So just because you have grad f is equal to lambda grad g does not mean that you have a maximum or minimum there. It just means this is one of your points to check. And in all the problems you look at in your calculus classes, you only have a small number of points to check. So where have we seen in our class something that we want to maximize or minimize? Linear programming problems. So we have an objective function, right? And then we have your constraints, basically ax equals lambda. I'm sorry, ax equals b. What we want to do now is we want to get into multi-objective linear programming, where you have more than one thing that you care about maximizing or minimizing. And we want to see how to handle that. And there's a lot of different ways. The first is we want to generalize Lagrange multipliers. Has anybody seen the generalization to what happens if you have multiple constraints? So subject to G1 of x equals C1 and G2 of x equals C2. Has anyone done that in their multi-class? So let's try to think what's going on. And so I will use the Rubik's Cube as an example. Are people able to see this? All right, it has lots of different colors. Let's look at the patriotic red, white, blue. Okay, let's imagine one of my constraints is I have to be on the white pentagon. And another constraint is I have to be on the blue pentagon. So if I have to be on the white and the blue pentagon, what does that mean?
You're on the edge.
I've got to be on this edge over here. So if I'm constrained to be on this right pentagon, the normal is going to look like this, coming out in this direction. If I'm constrained to be on the blue, the normal is going to be coming out like this. Now let's think about what's going on with this line. I have these two directions. There's 3 dimensions in space. The line is one-dimensional. So I can view this line as basically all things that are perpendicular to a plane. So the two normals here are going to generate a plane. And this line is going to be perpendicular to that plane. So if you think about it, this is going to give you one normal, grad G1. This is going to give you another normal, grad G2. And the claim is that grad F should be lambda 1 grad G1 plus lambda 2 grad G2. Another way of looking at this is initially, when I look at just G1 of X equals C1, I lose one dimension from this constraint. And so the normal is giving me that missing direction. You know, the tangent space has 2 directions, and the normal is the third. Over here, I also lose a direction. I have 2 directions. And so when I look at these two together, if I have to be in both of them, I've only got one direction to be in. So I have to be in that one direction, so I've got to be perpendicular to the thing spanned by the other 2. There's lots of ways that you can look at this. We basically, instead of saying, in the simple case, we were saying before, grad F had to be a multiple of grad G. That's really not the right way to view it. The right way to view it is, it can't be in the tangent space. Well, if the tangent space is 2 dimensions, and there's 3 dimensions total, there's only one direction remaining. But as you go higher up, as you have more constraints, the tangent space becomes smaller dimensional, and now there's more directions that are available. So really, the better way to view this is, yes, this is correct, but what I'm really saying is grad F can't be in the tangent space. Oh, the only direction that's left is the normal, which is the direction of grad G. So grad F not in tangent space implies the above. This is this true statement, but then we can write it like this. So a lot of times it's just, how do you want to write things? If f of x is x to the n, what is f prime of x? If f of x is g of x to the n, what's f prime of x? G prime of x. Or we'll do dg dx. Or d by dx of g of x. There is over here a d by dx of x. What's d by dx of x? We never bother to write it. But it's really there, and if you know it's there, it then explains where this g prime is coming from when you look at, when you look at what's going on over there. Right. So we're not going to really use too much of Lagrange multipliers, but this is something that you should be aware of. The subject is more useful than you might initially think. It does apply to more than just one constraint. It generalizes in a very natural way. All right. So what we want to do now is we want to consider multi-objective linear programming problems. So, multi-objective linear programming. So we still have ax equals b. We have x is greater than or equal to 0. Think of this maybe as it's the food problem. We're not allowed to regurgitate. And initially, we want to minimize cost. C transpose x. Can you think of anything else you might want to minimize? Or maybe maximize? Some food tastes better than others. When I was at Yale, the dining hall workers wanted the rights to experiment. There was not strong support among students for this. My favorite example was the ice cream sundae bar with cream cheese, because they were out of marshmallow, and well, cream cheese is white and marshmallow is white.
That's good.
Yeah, you don't. I spent 6 years in restaurants. You do not prepare meals by color coding. So you might want to include something about taste. So, or instead of taste, instead of maximizing taste, we would want to minimize disgustingness. Minimize cost, minimize disgustingness. I remember we were finally able to convince Princeton to always have pasta at dinner. And then after another week or two, we were able to convince them to have sauce with the pasta. It was a two-step process. So we'll make that C1, we'll make that C2 transpose X. Another thing you could do is maybe you are trying to buy a house. And maybe you want to minimize the cost of the house. But you might also want to maximize how much space you have. You might care about the location. How far is it from where you're working? You have lots of different factors. And so the question is, what is going to be the best choice for you? And so over here, we have to decide, how do you want to deal with these two different constraints? What do you think might happen to the cost as the meal tastes better and better?
Goes up.
It probably goes up. Are you willing to pay a little bit more? Anybody ever read the Origami Yoda books? They're actually quite funny. And I was listening to them recently with my kids when we went to Boston, and in one of them, they have a field trip, and it's a terrible day. If it could go wrong, it's gone wrong. And they finally decide, after the bus has been broken down for an hour and a half, they're going to stop at the first place. It's a Wendy's. They're going to call in the order. And the kids, we're starving. Can you supersize the meals? And the principal who's on the bus is quite concerned with district funds. And she's got a busload of kids. Does anybody know how much it costs to supersize a meal? And the whole bus yells out simultaneously, 39 cents each. All right, fine. For 39 cents each, the cost is negligible. Supersize everything. What if it was $3? What if it was $3 each? No. And so there's going to be some kind of transition where you're willing to pay a little bit more for a little bit better taste, but at some point it's too much. Similarly, you might pay a little bit more for a house that has a better location. What do you think most people care about when they try to buy a house? They care about what?
Safety.
Safety is one.
Square footage.
Square footage, but something else.
School district.
I'm sorry?
School district.
School district. Right? School district is one of the most important things people care about. So if you look at the capital of the evil empire, New York City, right? A lot of people work in the evil empire. How many people who work in the evil empire in high-paying jobs live in New York City? Not many. Where do they live?
New Jersey.
New Jersey, Connecticut. They live far away. Right? And sadly, a lot of Connecticut has been taken over by Yankee fans. It's sad. Right? New Jersey, it's fine. I mean, hell, even the New York sports teams often play in New Jersey anyway, so that's fine. Why do they live so far away?
Cost of living.
Cost of living is smaller there. What else?
Bigger houses.
Bigger houses. You have more space, bigger houses. What else?
The schools get more funding.
Schools get more funding. You have a lot of, the school districts are actually pretty good as you go further out. Sadly, a lot of the schools in the city are not as good. And so a lot of people choose to have a long commute, because they would rather have a bigger house, they would rather have a better school district, but they then spend a lot of their day going back and forth. Is it worth it? One of the nice things of being a Williams professor is, it's a 20-minute walk from my house to the office, and that includes walking directly through the elementary school to drop off my daughter in the morning. And I can adjust my schedule so I can be there for their games. And we can start the 7th graders on applied sabermetrics. It's wonderful. When you spend an hour and a half each way, that's a significant amount of time. A lot of people choose to make the sacrifice, a lot of people don't. How should we deal with the fact that we have two different things we care about? Yes?
There would be a third function that represents the utility between what they are consuming.
Okay, so we basically want to have these coming in as inputs into a utility. Are you a double major?
A little bit.
A little bit?
Well, not in econ.
Okay.
I dabble in econ and relativity.
No, good. That's good. It's much better to just dabble in econ. No, just when you use the word utility, that was the right word to use. I remember when I was an undergraduate, we had to do the function to get a bound for something in complex analysis. And my teacher wrote down the answer, and I raised my hand, and I said, that answer can't be right. The units don't work. The what? I'm sorry. The degree of homogeneity in the parameter A is wrong. Oh, yes, you're right. And so in mathematics, they'll talk about things like this. But for me, with a physics degree, if x is in meters, which are the units of AB? 1 over meters. So I can immediately figure out, okay, so this is meters, meters to the 4th. So this should be something in meters to the 5th. So what should be the A dependence? Because if I'm integrating out the x's, what should the A dependence be? If I have to get meters to the 5th. So x is in meters. A is in 1 over meters.
So it should be something 1 over a to the 5th.
It should be something 1 over a to the 5th. It should be some constant over a to the 5th. So for those of you who are taking like the math GREs, here's a way to quickly eliminate a lot of answers. Just functional form, what does this have to look like? I prefer to say units, I prefer to think of it in terms of units. Mathematicians often like to talk about homogeneity. It's the same thing. Utility is the right word. We've got to somehow create a utility function that depends on these two things. The higher the cost, the less happy we are. The more disgusting it is, the less happy we are. The key is we need to figure out how to do a trade-off between cost and disgustingness. Any thoughts? So you always want to keep things simple. What's the simplest thing you could think of?
Oh, okay, well, I mean, the simplest is to sum the two.
Good.
And then, I mean, say if you want, the next complicated thing would be then to add an additional constant to each of them.
To add a constant?
Well, sorry, not add. Sorry, put a coefficient on.
Right.
on each
So the
of them.
simplest thing is to treat them equally. And if you have no other knowledge of the problem, treating things equally is the best thing you can do. And then you can start putting in some weights. So if I weight this by, say, W, what should I weight the other one by?
A little less than W.
I'm sorry?
A little less than W.
1 minus I.
1 minus W. Think of it as you have 100% to assign between the two. Whatever you don't assign. Now, you could, of course, weight this by anything you want, but you can always rescale to make the weight sum to 1. What should I assume about W? Less than 1. Well, it could be 1, but if it's 1, then it's a little bit ridiculous because it doesn't matter. What else should I assume about W? Probably greater than 0. So I would probably assume 0, less than W, less than 1. You know, maybe allow myself something like that to just have it collapse. And that's it. That's now multi-objective linear programming. Everything else is the same. So where's the beef? Where's the meat? Where's the difficulty? Yeah.
Minimizing that is harder than minimizing either of those separately.
Nope.
Oh, okay.
Because this is just the same as, let's let C be the vector WC1 plus plus 1 minus WC2. It's just it's a linear programming problem. I've just changed what my C is. Where's the difficulty?
Calculating W.
Yeah, determining what W is. Right? That's the difficulty. What weight do you put on? How do you determine how much one thing means to you versus another? Yes?
Is that even in the
For certain things, it is beyond the scope of this class. For other things, math major versus Red Sox versus Yankees, some decisions like that are within the scope, but most of the time, absolutely beyond the scope of the class. It's individual preference. I had a student when I was at Princeton who wanted to protest something that she really believed strongly was wrong. And she wanted to devote all of her time to it for a couple of weeks. And I said, you are welcome to do that. I will have all of your homework and exams pushed back to the very last moment I can. You're responsible for getting it done. You can allocate the time how you wish. I'm happy to meet with you. And you have to decide, how much is something worth to me? How much am I willing to trade on this for that? I had some friends in Yale who ran up huge credit card debts. And they said, I'd like to live nice now. I'm going to get a good job when I graduate. And so I'm going to run up the debt now, have fun as an undergraduate, and then when I make the big salary, I'll be hit a little bit, but I'll spread my purchasing power a little bit more uniformly across time. For a lot of people, there's a lot of illogic in how they do weights. It's not necessarily transitive in terms of what you prefer. So determining what the weights are is extremely challenging. And it is absolutely essential if you want to do something like this. If you want to figure out, well, I want to have a large house, a good school district, good location, many bedrooms, fireplaces. You start putting in all these things and then that's wonderful. You've just described the unicorn. Okay? It does not exist. I'm sorry for those of you who believe that unicorn. So, which matters more? How much are you willing to sacrifice? How much are you willing to trade? All right. Any questions about this? What's nice is once you have the weights, you just run the program as before. So there's no challenge from that point on. The difficulty is figuring out what those weights should be. One of the things we might do later in the semester is there's another thing you could do where we don't necessarily know what the parameters are going to be. So what if you have some uncertainties? How do you handle linear programming in that regard? So one of the famous problems is the oil supply. You have a couple of places that produce or refine oil, and you have cities that demand oil. But the oil demand may not be constant. What could greatly change oil demand?
A substitute for oil.
So one is a substitute for oil. So we'll assume that we don't have an incredible advance in, say, solar technology or nuclear disposal. So let's assume no technological advance. But what could easily happen?
Seasonality.
Seasonality. And so some of that you could plan in, but you could have unseasonably warm or unseasonably cold days, which could greatly change. Anybody here remember getting any emails from Williams about power? Where there is a huge load on the grid right now. If possible, please do not use any electricity. These are more likely to be sent out during the summer months, when it's a really hot day, a lot of air conditioning is being run. And so what would you do? Oh, sorry. Yeah, for those of you who are staying on campus, yeah. In professors' offices and administrative buildings, yeah, air conditioning is being run. So you might actually not know what all these parameters are. You might not know what the demands are. There are ways to handle that, and we will possibly talk about those later. So I want to end today with one of my favorite mathematical arguments. How many of you have seen Vandermonde Determinants? That's a one. The cultural reference for today is there is a Seinfeld character who has a fictional company whose name starts Van something.
Vandelay.
I'm sorry? Vandelay Industries. And the character is? No, but who?
George.
George Costanza. Okay, excellent. Vandelay Industries. Do you remember what they sell?
No.
Sometimes I think they're importer-exporters. Sometimes they sell latex. Vandermonde determinants are absolutely wonderful. And they will allow us to solve an interesting question. So imagine I give you a matrix A that has n columns and m rows. And I want all of the columns to be independent. And I want n to go to infinity. Is it possible to have all the columns independent as n goes to infinity? So all the columns will be linearly independent. Okay, why not?
Because when n is greater than m, they can't be all linearly independent.
Right, because the columns will live in Rm. So what's the maximum number of columns I can have that are linearly independent? M. So the question, construct a matrix such that any m columns are linearly independent. Can that be done? And this is actually quite useful for us because when we go back to solving linear programming problems, one of the things we care about is basic solutions. What's a basic solution? Well, it's a choice of x such that the non-zero components correspond to linearly independent columns. So one of the questions is, how many linearly independent combinations can I have? How bad could things be? To just give you a sense of how bad things are. We're not going to prove the runtime, but I want to give you a sense that maybe it is possible that we could have a matrix where any set of m is linearly independent. If so, that means we have a lot more candidates for feasible solutions, and the problem could take longer to solve. Okay? Maybe, however, it's extremely rare for a matrix to have linearly independent subsets of size m. That maybe, yes, you can construct it if you're very careful and align everything, but maybe a generic matrix, this won't happen. So what does your intuition tell you? Do you think a generic matrix will have any set of m columns linearly independent as n goes to infinity, or do you think it's very rare for a generic matrix to have this property? Any thoughts? I hear mumblings, but not loud mumblings. Often. So it turns out almost any matrix you write down will work as long as you are a smartass. If you just put down things with integers, it's going to fail eventually, I think. But if you put down arbitrary real numbers, it's going to succeed. The worst question I ever had to grade when I was a grad student was written by the lead professor for linear algebra. I was just one of the grad students teaching one of the sections. And they gave the students 3 vectors in 4-dimensional space, and the instructions said, give a 4th vector that's linearly independent. Almost any vector you write down is linearly independent. And the instructions did not say prove, it just said give. And so all the grad students either just marked it right or had to check. And I will leave it as an exercise to figure out what we did. Yeah. Let's construct the matrix. Let's choose A1. We can choose anything we want for A1. If we want to choose A2, how hard is it to choose A2?
Just not multiple.
Not a multiple of A2. Okay, so A2, not a multiple of A1. So if you look at Rm, is a generic vector not going to be on a line in Rm? Yes, not a problem. All right, now we need to choose A3. What do we have to worry about A3? Okay, so A3 not in span of A1, A2. Is that hard? The span of A1, A2 is a plane that has, hypervolume 0. So we keep going, we get to AM without any trouble. Now things get a little bit more interesting. No matter what we put in now, it's going to be linearly dependent with A1 through AM. But that's okay. We just need to make sure that any set of m vectors are linearly independent. So what do we need for AM plus 1? Yes?
It's not in span A1 through AM minus 1. Or in the span of any m minus 1.
Of any m minus 1 of the A1 through AM minus 1. How many ways are there to choose? I'm sorry, of the AMs.
Is that AM plus 1?
AM plus 1, yes. So AM plus 1 is not in the span of any of the M minus 1 A1s to AMs. So there are M ways to choose M minus 1 of these. It's the same as choosing one to exclude. And again, each of those is going to be a plane. What's the volume of the union of finitely many planes? It's still 0. And then we choose AM plus 1. And then we choose AM plus 2. And at each moment in time, we throw away finitely many planes. And the union of finitely many planes is still going to be 0 volume. So this proves that almost any choice works. So if you just choose the vectors at random, it should work. All right. So this tells us that not only is it possible to do it, but it's the generic case. It's what you would expect. What I want to do now is I want to show you an explicit way to construct a matrix that works. So this is the Vandermonde. And it's absolutely wonderful. So consider 1, x1, x2, xm minus 1, x1 squared, all the way up to x1 to the m minus 1. 1, x2 squared, all the way up to x2 to the m minus 1. And then 1, xm squared, all the way down to xm to the m minus 1. So consider this matrix. So this matrix is a function of x1 through xm. I can calculate its determinant. So the determinant of V is some function of x1 through xm. And what we want to do is we want to figure out what is that function. Well, what would happen if x1 equals x2? It's got to be 0, because if x1 equals x2, we have two columns that are the same. What if x1 equals x3? 0. If any x equals any other x, it's 0. So this is a multiple of the product 1 less than equal to I less than j less than equal to m of xj minus xi. So we know the determinant of V is some new function of x1 through xm times the product 1 less than equal to I less than j less than equal to m of xj minus xi. So when I expand this out, this is a polynomial. What's the degree of this polynomial? It's m choose 2. I have to choose two numbers that are distinct. So the degree is just m choose 2, which is m plus 1 over 2. Now let's look at the matrix. If I look at the diagonal, I've got this is degree 0, degree 1, degree 2, degree m minus 1. And if you look, because when you expand out the determinant, you're always going to have something in the first row, something in the second row, something in the third row, so they all have the same degree. So the degree of V is 0 plus 1 plus 2. Oh, have I done something slightly wrong?
M minus 1. It's M choose 2. It's M.
Oh yeah, I wrote the wrong. Sorry, I wrote the wrong thing here. Thank you. It's m times m minus 1. Good. Plus m minus 1. And this is just equal to m minus 1 times m over 2. If you haven't seen why this is the case, just write the numbers backwards. And you'll see each time you sum, you get m minus 1. You have m terms. So the sum of twice everything is m times m minus 1, then divide by 2. They have the same degree. So if they have the same degree, what can you say about this? It's constant. All we need to know is one little fact about this constant number. What do we need to know? It's, yes, it's non-zero. If we can prove it's non-zero, we're done. If it's zero, we're screwed. So what I like about this is we do not need to determine the constant exactly. We just have to prove it's not zero. So to prove that it's not zero, what we can do is we can look at special values of the x's. Let's take x2 much, much larger than x1. Let's take x3 much, much larger than x2, and so on and so on and so on. And if we take the x's to be growing at phenomenal rates, then the main term in the determinant is going to just be the main diagonal. And that will be enough to show that it's non-zero. So imagine you take x1 equals 1, x2 is 10 to the 10, some tremendous number of times. x3 is x2 to the x2 to the x2 some tremendous number of times, and so on and so on and so on. These numbers are growing so astronomically large. And if you want, put in an m over here to make it, as a function of the matrix size. These numbers are growing so large that there is no way all the other terms can overcome the main diagonal. And this will prove that the constant can't be zero. You can actually do even better. Because it's going to be dominated by that main diagonal, if I multiply everything through, then I'm going to get the coefficient of xm to the m minus 1, xm minus 1 to the m minus 2, all the way down to x2 times 1, is going to have a coefficient of 1. And you should be able to use that to get like the leading term over here, and to get, I think, that the constant is 1. I don't really need that. I don't really care about that. All right. Any questions about this? So the purpose of this is to just give you some sense of how long the simplex method and stuff could run. That it's actually the most likely case, if I give you a matrix, that any set of m columns will be linearly independent. And there will be a tremendous number of feasible solutions. And what I want to end with today is linearizing polynomials. So imagine I have something like the product I less than equal to m1 of xi, and then the product m1 plus 1 less than equal to j less than equal to m2, no, it's to m, of 1 minus xj. I can view this as I start showing the first m1 movies at a given time, and I'm not showing the other movies. I don't start them. So I'm dropping all the other subscripts. I'm dropping screens. I'm dropping time. I'm just looking at a product like this. This is something that could arise. This could be telling me how many people might be coming in to my movie theater at a given amount of time, at a given moment. These are the movies that are starting. These are the movies that aren't starting. I have some idea of how many people I might need to be selling tickets. This is clearly not a linear function, but we might want to deal with something like this. One way to deal with something like this and to linearize it is, if I look at this, all I care about is the values. What are the possible values of this product? So the x's are either 0 or 1, so what can you tell me about the possible values of this product? It's 0 or 1. So what that means is I can replace this monstrosity with a binary variable. And what I could do is, if x1 plus xm1 plus 1 minus xm1 plus 1 plus dot 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 plus 1 minus xm, if that equals m, then x equals 1, else x equals 0. We know how to do that. The only way this product can be 1 is if all of these are 1 and all of these are 1. So that means these x's are 1 and these x's are 0. We know how to do this with statements. So basically, if this sum is equal to m, then I choose x1 to be 1. We know how to code that. So you can actually replace non-linear terms like this with linear terms. This is the power of binary variables. It is essential that products of binary variables are still binary. That's the key fact. If you had things other than binary, that would no longer be the case. So this is why binary variables rock. All right, this is a good time to stop. Have a good rest of the day.